in my talk, I'm going to focus on lifelong learning systems, both models and how we design hardware systems out of that. And particularly, we'll focus on how these systems are designed using different neural plasticity mechanisms. This work is in collaboration with several of my students that are listed in here. Nicholas Soros has done one of the key models that I'll be presenting today. So before I talk about the models, I wanted to give a brief introduction to what lifelong learning is and kind of walk you through some of the challenges or the features that a lifelong learning system needs to have. So if we think of current artificial neural networks, when they're presented with new learning tasks, they are often prone to forget what they have learned previously. And we would like artificial systems to rapidly adapt to new conditions without forgetting previous knowledge. And we would like to see continuous improvement in performance while executing previously learned tasks and when new tasks are introduced to the system. So here is a cartoon on the top that you can see. Let's see if I can use my pointer. So the cartoon on the top, you could see that there are these different tasks. A model could be introduced during its lifetime. And the one on the bottom shows how the performance of this often conventional AI model drops when a new task is introduced because it has forgotten what it has learned in the past and is not able to adapt to new tasks. Whereas what we would like to have in a lifelong learning model or in an AI model is when a new task is introduced, there could be a short refractory period, but the model kind of picks up and improves its performance. And even when a previous task is reintroduced to the model, the performance kind of improves over the past performance. In order to achieve this, the model needs to operate at varying timescales and frequencies. So recently, a large group of us published an article, a perspective article on how biology can inspire in designing these lifelong learning machines, where several of us were part of this DARPA Lifelong Learning Machines program. So in this we define lifelong learning and its key features. Here we say learning is really a defining ability we see in biological systems where experience leads to behavioral adaptations that improve performance. And one of the key insights in here is that there are several biological mechanisms beyond neural plasticity, whether they're neural mechanisms or non-neuronal mechanisms that can improve our ability to create highly functional learning systems, or particularly lifelong learning systems. So I'll kind of give you a quick walkthrough on the key features we identified in this article as the features that are required to design a lifelong learning machine. So the cartoon here on the top is showing a lifelong learning agent that encounters an unpredictable stream of training episodes. And it is intermixed with situations where it must apply recently or previously learned skills. So in this specific example, we have a robotic arm that is being trained to perform a variety of tasks and is subsequently able to select from its database of learned skills and apply it to different situations it encounters. So the 6 features we have identified are shown in the bottom cartoon here. The first one is from left to right, if we see, the first one is transfer and adaptation. What does that mean is the ability of the model to apply previous knowledge to new tasks and to quickly adapt to changes in the task or the environment. So for example, in this context, the system is trained on task B, where it's packing objects, and is subsequently able to apply the learned skills to facilitate learning of similar but not identical task. It could be different shapes or sizes of the object. The second feature is overcoming catastrophic forgetting. So if we look at the current AI systems in this gray block in here, suffer from catastrophic forgetting, as I mentioned earlier. It's the inability to learn new tasks without degradation of performance on one's previously learned. So in this example again, the system is first trained on task A, then on task B. And after task B training, if the model is still performs well on task A, then that is what we would like to achieve in this lifelong learning machines, to retain the knowledge that it had from previous tasks. The third one is exploiting task similarity. So here, rather than learning a monolithic representation of a task, we want the model to decompose it into subtasks that can be applied when learning new tasks. Again, in this example, the positioning action here by this robotic arm, which is learned as part of the task B, which has other elements, right, like such as gripping and translation. And this positioning action is directly transferable to task C, allowing it to reuse this skill. The other task B skills, gripping and translation, are less applicable to task C. And the next one is task agnostic learning, in which the agent has the ability to solve a problem without being aware of when the task switches are happening. So in this example again, the gripping action that it learned during task B training is applicable in the current scenario as well. The noise tolerance is the ability of the model to execute a task despite noise that was not present during training. And in this example, again, the system is trained to perform a task without any distractions or any irrelevant activity that is not critical to its learning. The last one, but a critical one also, is the resource efficiency and sustainability. Here we are saying the model's ability to continually learn new tasks with limited system resources, whether it is the compute or memory resources. So if we have to formulate this problem, it is really to learn from the model should be able to learn from a family of tasks, where each task is represented as T here and presented sequentially, and X represents the learning samples, and Y here is the output targets, and T is a task identity that is shared across all tasks. And our goal here is to minimize the overall loss across all these tasks. So obviously, it's not a trivial challenge to kind of design a system with all these features and able to learn continuously through its lifetime. And think of bringing these features to, if you want to have these lifelong learning capabilities at the edge, because a lot of applications that we think of for lifelong learning are in the cases of, are often deployed on the edge or in resource-constrained environments. So that brings an additional set of challenges where I think several of the speakers over the last couple of days have talked about how to improve performance or efficiency in these types of environments using neuromorphic computing. Because when we are thinking about the learning at the edge, you also have to have this real-time learning capability. It needs to be able to make these decisions with low latency and have to use very few memory and compute resources and under highly constrained energy budgets. And this is where we think taking the neuromorphic approach could offer us some reprieve. In a sense, again, several of these features or efficiencies of the neuromorphic systems are covered over the last couple of days with different kinds of device models. They're inherently considered energy efficient. You're able to use different kinds of plasticity mechanisms when realizing a neuromorphic system that could be beneficial for lifelong learning. And the ability to have memory and compute co-located can give us, again, orders of efficiency in terms of resources. And on the right here, I show some example models that our research group has explored, models that are inspired by different biological regions that are shown on the x-axis, and the capabilities of the algorithms and their ability to solve either spatial or spatiotemporal or self-organizing models. So the one we are going to focus is on the rightmost here, on the neural plasticity and how that kind of supports the lifelong learning. So for the next few minutes in the talk, I'm going to talk about the plasticity, neural plasticity mechanisms that we have used to build some of the models. So before I go into that, I just wanted to again give a quick overview of the different mechanisms that researchers are exploring right now to build lifelong learning models. We can kind of group them into these three high-level categories. One is dynamic architectures, where you could think of structural plasticity mechanisms such as neurogenesis, synaptogenesis, or pruning, and so forth, or context-dependent gating. So the idea is that you add additional neural resources to the model for future learning, or you can selectively use specific resources on certain tasks. And in order to, if you're using these kind of mechanisms, you would typically require task knowledge or meta-learning for the model to perform efficiently. But when we are using neurogenesis or any kind of structural plasticity in some contexts, if we do not have any bounds, this is going to be very challenging when we are thinking of hardware realizations or even computational models. The second group of mechanisms that are used in, to achieve this continual or lifelong learning is plasticity-based. And in here, you can think of synaptic consolidation, metaplasticity, local learning, any of these mechanisms. And here, plasticity can regulate the online learning and protect the information that is at the synapse level. And it kind of can use different different mechanisms to kind of estimate a synapse's importance. And by playing with the plasticity, it could be a parameter in the model, you could reduce the learning on future tasks or increase the learning depending on what we are trying to solve. And the third group of mechanisms fall under replay. So the idea here is that the network or the model is introduced or experiences what it has learned in the past during an offline learning phase. You either replay this past experiences in different forms. Either you could use pseudo rehearsal or rehearsal of the full task, which is not very efficient. But in this context, you could have this significant overload on memory because you need to store all these past experiences. It can be quite expensive on the system. So buffer-based approaches can be challenging in here. Researchers sometimes use generative models to recreate the prior experience as well. So in all these contexts, there is an argument that it is not enough to just use dynamic architectures or plasticity to achieve lifelong learning. We definitely need to incorporate replay in some form in the system, especially when the model could be introduced with multiple tasks over its lifetime. So in this talk, I'm going to focus on the center bucket of mechanisms, the plasticity ones, a few of them, and how we used in our model. So we kind of highlight this also in the research article I mentioned earlier. The y-axis or here shows the different biological mechanisms. As I mentioned, structural plasticity ones or just plasticity mechanisms and how they support the key features required for lifelong learning. And you can see that there is no one mechanism that can support all the key features required for lifelong learning. And we need to use a combination of these features. And depending on the type of environment we are kind of deploying the models, we need to identify what is the right mechanism. And also, in some cases, having a dot in here supports that specific key feature, but the degree at which it can support also varies. So there's a lot to be discovered in here, and how efficient each of these mechanisms can be in achieving a certain feature. So with that, let me talk about the mechanisms we have used in our model. The first one is metaplasticity. So here, metaplasticity changes the physiological, or the biochemical state of neurons or synapses. In a sense, if you look at this cartoon on the top, a depotentiating event, when you have a potentiated synapse and there is a depotentiating event, it reduces the synaptic strength. So after depotentiation, an identical nerve impulse produces a much smaller response, as you can see on the top. Over time, what happens is this potentiated synapse becomes less plastic, which means it becomes less susceptible to depotentiation. And this is what we call a metaplastic change. And once this metaplastic change occurs, or metaplastic stabilization happens, if you look at the bottom plots, the same depotentiating event causes little or no depotentiation. So in this case, what's happening is metaplasticity is helping us to protect this potentiated synapse against disruption. So what that means in the context of continual learning is that it is protecting the synapse from new learning. And the second mechanism we look at is synaptic consolidation. And synaptic consolidation refers to a form of this long-term plasticity, where information is stored in the synapse without being affected by future learning. And to capture this, we kind of realize the synapse with two components, where in the early phase, there is learning happening, and in the later phase, there is consolidation happening in the model. So in the early phase with weak stimulation, the model is still able to learn in this context, and with strong stimulation in the late phase, you could see that it is maintaining its prior knowledge. So consolidation acts at a much longer time scale than plasticity induction, and it can act in conjunction with other plasticity mechanisms to allow a synapse to remember its past knowledge. So the idea was, as I showed in the table earlier, can we use these multiple plasticity mechanisms to cooperate and support continual learning? So if we look at an example here, we have three tasks: task 1, task 2, and task 3. Let's say task 1 wants to train the weight very high, and task 2 wants to train the weight low, and task 3 does not have an impact on the weight. So without metaplasticity or consolidation, weights learned during prior tasks obviously will be quickly overwritten. Whereas on the right here, we show with metaplasticity, weights will be overwritten, but at a much slower rate. And with just consolidation, we see weights will be overwritten quickly, but the network will be trying to return to prior weight values through decay. And when we combine both metaplasticity and consolidation, we can see here that the rate at which a weight is overwritten slows down drastically, and it allows consolidation to return the weight to perform to prior values from past tasks. So in a way, metaplasticity is restricting the synaptic updates of important synapses, and consolidation is capturing information over a long time scale. So by combining these two mechanisms, we thought we could prevent or help the network avoid this catastrophic interference. So with that came this idea of this model. We call it TACOS. And this was actually realized in a spiking neural network. This is the first spiking neural network that is shown in a continual learning model. And particularly in a task-agnostic scenario. So what we did was we used this combination of plasticity mechanisms in this model, and the spiking neural networks, the idea is that they could offer us more energy efficiency, but also they're more natural to realize these plasticity mechanisms. The local plasticity, again, mechanisms will help us with low communication overhead because we have sparse updates and does not rely on the task knowledge. And the complex synapses, which I've talked about, help us with this catastrophic interference. This is the model example. The network is configured for 200 neurons per hidden layer. We have 2 hidden layers in this case and a 2 neuron output layer. And we incorporate metaplasticity, as you can see in this example. See. So the way we implement it is using this plasticity factor that we are computing based on this equation. And what we are trying to do is plasticity is decreased for neurons that had high activity levels at the end of a sample. And we use this M, which helps us identify what would be the ideal metaplastic rate that impacts a specific model. And similarly, we incorporated synaptic consolidation in the same network. And the way we incorporated it is by using 2 components, a fast component and a slow component. The fast component is driven by task-specific learning and is regulated by metaplasticity, and the slow component consolidates information on a longer time scale. And this is the complete TACOS network. And we have evaluated this on SPLIT-MNIST and FMNIST tasks. And our network, TACOS demonstrates much higher accuracy over some of the other state-of-the-art models, and it's consistent across both samples. And the overhead is slightly higher than some of the other models with just metaplasticity or consolidation, but it is still lower than some of the state-of-the-art models. And the most important point I want to highlight is that in this model, we only show the data sample once, as in the performance that I'm showing in here is with 1 training epoch. So that is a significant, plays a significant impact on the network performance, and resources as well. And we did some analysis on the plasticity stability of the network, and we see that the network performs, in general, I think TACOS allows a much greater degree of plasticity because we kind of looked at the weight change in use after learning a single task and after learning the final task. And we also see that it is much better retention in knowledge by looking at this higher cosine similarity across different metaplastic rates. And we also did energy consumption analysis for this across 3 different technology nodes. And we see that metaplasticity is slightly expensive, at least in our current implementations, compared to consolidation-based mechanisms. So there is some room for improvement in how we are realizing these kinds of mechanisms. There are some challenges with TACOS. It's phenomenal in terms of able to achieve this in a single epoch, but it does not scale well with variable sample sizes because there's a time lag in when metaplasticity kicks in. And we cannot always fine-tune metaplasticity beforehand. And in some cases, this could reach to having the network in a frozen state. So what we are exploring right now, this is really a very early analysis, is we want to address these shortcomings by, instead of using a fixed decay rate, we are trying to use a dynamic decay that would adjust the model and not having this prior knowledge of how to tweak this metaplastic factor. And it shows some interesting results on how the model works with increasing number of samples with different metaplasticity rates. When the metaplasticity is high, low, or normal, how the performance is varying with fewer samples versus higher samples. Again, we are still really exploring this, and I think this would have a better way to kind of scale the model for tasks, for increasing number of tasks. And I want to quickly show that we have implemented a digital architecture for this continual learning framework. It is actually going to be presented in a month at ISCUS. And it does not have all the features that I've shown in TACOS, but it has some of the metaplasticity features, and we had to make it lighter to realize it on a low-end embedded platform. So we have different processing elements that are introduced in this model with 8 metaplastic synapses. And we had 4 KB SRAM to store the synaptic weights. So we have you can see each processing element consists of a lift neuron, a metaplastic block, and a synapse memory. And we had to do several optimizations to make it hardware friendly. We had to use this bilinear function and dyadic scaling. And those are easier implementations when we're thinking of the hardware. But what happened was we said, well, this cannot fit in a hardware with this kind of size, so maybe we can do quantization. And when we did quantization, obviously, as I think Ann and several others presented earlier, it can have a significant degradation in performance. So what we did was, so if you can look at it that at 8 bits, the network performance degraded significantly. So one of my students, Vedant, was looking at this, and he kind of saw that this distribution of the weights across the network and saw this high concentration near 0, and then tapered, the density is quite tapered at higher values. So we kind of used a dual fixed point in order to improve the performance rather than using a single precision for all of the weights. So with that, when we use the dual fixed point, we see that the performance is actually even higher than using 16-bit precision in some of these cases. So that helped us significantly reduce the overhead for the network. I think in the interest of time, maybe I will not be able to cover this second hardware model I wanted to show, which was more a mixed signal implementation. We had both digital and mixed signal implementation of this for continual learning, but I can talk offline about this. So in summary, I kind of show how plasticity mechanisms can help us achieve continual learning capabilities. Particularly, I showed how to mitigate catastrophic forgetting or learning in a task agnostic setting. And this is kind of the first spiking neural network demonstration that is able to do this by training in only a single epoch. And we are currently working on a memristor-based implementation. And actually, we'll have our first tape out come out in a month for the TACOS framework. And in general, what I have presented today, the problem is in the context of spatial data, and the complexity kind of grows significantly when you're thinking of temporal data streams. And even in mainstream machine learning, this is quite a big challenge right now, how to process these temporal streams and achieve continual learning. And thank you all for your time, and thank you to my amazing group of students and the sponsors who make this work happen.